Alright, so today we're going to talk about systems of equations, which we've done systems of equations like two linear equations where you can solve by graphing, you can solve by substitution, you can solve by elimination. And there was one example on the county interim assessment that was a system of equations too. It was a quadratic equation and a linear equation. And you had to find out where the two intersected, okay? That was the only thing we've ever done with nonlinear systems. So I want to do a few more examples because this is something that you're probably going to see on the FSA. So that's what we're going to take notes on today. Solving nonlinear equations. I should say solving systems of nonlinear equations. I will be taking this up for points. Also, several of you have been absent and owe me notes from Algebra Nation stuff, or notes yesterday. We took notes on trig that was not Algebra Nation. I've been taking that stuff up to give you a grade because I've not been given homework, quizzes, and tests. So make sure you're getting that kind of stuff turned in. Alright, so my first example, I have x squared plus y squared equals 13. In this class this year, we have not done any problems that deal with an equation like that, where x is squared and y is squared. If you see this type of equation, this is a circle. Okay, in some classes, hopefully we get to do some circle stuff before the FSA, but in all of our classes we won't. But this tells you that you have a circle. And then x squared minus y equals 7. If I were to isolate the y on that, it would be y equals negative x squared plus 7. That would be a quadratic. So the one we did on the county interim assessment, it was a quadratic and a line. This would be a quadratic and a circle. So it could cross, it just depends on where the quadratic is, right? But say it was like this, we could have 4 different solutions. Because the solutions of a system are what ordered pairs do they have in common. So basically where they intersect. Well, we don't know how to graph a circle. We know how to graph a quadratic, but even if we knew how to graph both of them, there's no graph paper. And you need some tools to make a circle perfect, right? So we're going to solve this algebraically. So anytime you have a system of equations, no matter if it's a line, a circle, a quadratic, a cubic, a quartic, a quintic, no matter what kind of function it is, you can always use this method. Either in both of your equations, isolate your y, or isolate your x. It doesn't matter. Sometimes maybe they both already have the y isolated. Or maybe in one equation the y is isolated and the other equation nothing's isolated. So usually I just end up isolating the y. Sometimes it's done for you, sometimes it's not. In this equation, my x's aren't isolated and my y's aren't isolated. So I'm just going to isolate the y in both of them. Okay, so I'm going to do that first. Make sure it's the same variable in all of the equations. So for my first equation, x squared plus y squared equals 13. I'm going to isolate the y. When you have these circle equations and you go to isolate, when you do, you might end up with something a little crazy, but that's okay. You just have to do whatever you have to do to get it isolated. So if I want to get y by itself, the first thing I would do would be what? Subtract x squared from both sides. X squared minus x squared is 0. Bring down y squared, it's positive. So y squared equals negative x squared plus 13. Have I isolated the y yet? No. Now what do I do? Square root of both sides. And for now, I'm just going to take the positive square root, okay? So the square root of y squared is y. Can I take the square root of negative x squared plus 13? No. This is a binomial, so it's all or nothing, right? I can't just take the square root of x squared and not 13. If there was parentheses around this and it was squared on the outside, I could take the square root of that because I'd have two of the same factors. But I don't, so I'm just going to leave this as negative x squared plus 13. My y is isolated. Is there anything I can do to simplify the right side of that equation? No. Okay. So I'm good to go there. So now I'm going to go to my quadratic. This one will be a little easier. X squared minus y equals 7. And I'm going to isolate the y in this example, or in this equation. So what would I do first? Subtract x squared. X squared minus x squared is 0. Bring down the next term, which is a negative y, equals negative x squared, and then 7 is positive, so plus 7. Is my y isolated yet?
No.
So close, so close. What do I do now?
You divide it by -1.
Divide by -1. So negative y divided by -1 is positive y. Negative x squared divided by -1 is positive x squared. Positive 7 divided by -1 is negative 7. Like I said, if you start with two equations where the y is already isolated in both of them, super easy because you don't have to go through this step. Okay? Usually at least one of the equations will have an isolated variable, but not in this case. Okay, so once we've isolated the y, just like we did on that county interim assessment, I want to know where these two equations intersect. Where are they equal? Okay, so what I do is I take what y is equal to in the first equation and set it equal to what y is equal to in the second equation, because I want to know when those two equations are equal to each other. So I'll just say the square root of negative x squared plus 13 equals x squared minus 7. And I want to solve for x. Can I add this x squared to both sides? Not right now. I got to get rid of the square root sign or the radical sign, right? So what is the opposite of square rooting something? Squaring it. So if I square the left side to get rid of the radical, then I've got to square the right side. And I square that whole thing together, not individually. Now, I'm not taking the square root of anything. The only thing I'm doing, if something has square root and I square it, the only thing that does is get rid of the radical sign. It does not change anything under the radical. On the right side, I did not have a radical, though, did I? No, I didn't. So, this x squared minus 7 quantity squared, I'm going to go and write that out as x squared minus 7 times x squared minus 7. And I'll have to FOIL that to get rid of the parentheses, right? Nobody said this was going to be a short process. So on the left, nothing to do yet. Just bring it down. On the right, I'll distribute x squared times x squared. It's x to the 4th. X squared times negative 7. Negative 7x squared. Negative 7 times x squared is negative 7x squared. And negative 7 times positive 7 is positive 49. I could start moving some stuff over, but I'm going to clean up this left or the right side before I do.
Wouldn't that be negative 14 x to the 4th?
Well, it'll be negative 14x squared.
Okay.
Yeah.
Why do I keep doing that? I don't think that.
Yeah, I got to be careful about that. Because you were doing the rules for adding and multiplying all in the same thing, right? Okay, so now I'm going to get everything to one side of the equation, see what I have, and then go from there. There's a lot covered in this problem, actually. So I will add x squared to both sides. And I'll go ahead and subtract 13 from both sides as well. So on the left, negative x squared plus x squared is 0. Positive 13 and negative 13 is 0. So I'm going to put a 0. There's nothing left on the left side. On the right side, I have x to the fourth. Negative 14x squared plus 1x squared is negative 13x squared. And 49 minus 13 is positive 36.
Is that it?
Well, I'm trying to find an ordered pair of where these two graphs intersect.
Are you serious?
Have I found an ordered pair? No.
You have to set everything to 0, right?
Yep, I set everything to 0. Got that done. Can I use the quadratic formula to solve for x?
No.
Why not?
Because it's not quadratic.
Because it's not a quadratic. Oh my god, y'all learned something.
All you do, I know what it is. I know what it's called with the 4. It's, say the word, I can't remember it. I know what I'm,
Brooke's trying to say is, she remembers that my first term has a degree of 4, right?
yeah.
My middle term has a degree of 2, and my last term is a constant, a degree of 0. I can't use quadratic or completing the square of none of that because it's not a quadratic, it's a quartic. But I can rewrite it as a quadratic and then factor that way, right? Remember where we replace x squared with a? So we would replace x to the fourth with a squared minus 13a plus 36. Y'all remember this method? I don't have time to look it up in the spiral, but I can at the end if you want me to. It's called rewriting as a quadratic. And then I can factor this just like I normally would a quadratic. So we know a is 1, b is negative 13, and c is positive 36. I need two numbers that multiply together to give me a times c. A times c is
36.
positive 36. And I need two numbers that add together to give me b, which is negative 13.
Would it be negative 9 and
Let's try it. Sounds good. Negative 9 times negative 4 is positive 36. And negative 9 plus negative 4 is negative 13. Boom. Am I going to have to divide and slide on this one? Nope, because a is 1. So we have a minus 9 times a minus 4.
Now you equal them to 0.
Almost. Do I know what a equals or x equals?
X.
I want to know what x equals, right? I switched out my x to get an a so that I could factor it, but now I got to put the x back in. Because wherever we saw an x squared, we put in an a. So now wherever we see an a, we got to put an x squared. And then we'll set them equal to 0. So instead of a minus 9, it's x squared minus 9. Instead of a minus 4, it's x squared minus 4. Because think about it. If we did a minus 9 and a minus 4, if we FOILed that, would we end up with what we started with? X to the fourth minus 13x squared plus 36? No. But x squared minus 9 times x squared minus 4. If we FOILed that, first times first gives us x to the fourth. Last times last gives us positive 36. We could do the whole thing, right? And that would give us what we started with. Now, let me come over.
Don't you have to square root?
Yeah. Well, first I got to set them equal to 0, right? X squared minus 9 equals 0. And x squared minus 4 equals 0. Because I have to figure out what x is.
Plus 4
Right? So I'll add 9 here. X squared equals 9. I'm going to take the positive and negative square root of 9. So x equals positive negative 3. Right on? On the other side, I'll add 4 to both sides. So x squared equals 4. Square root both sides. I'll take the positive and negative square root of 4. X equals positive negative 2. I'm trying to find ordered pairs where this circle and this quadratic intersect each other. Have I found ordered pairs?
Yes.
I found ordered pairs.
Oh,
I found 4 different x values. Yep, that's what I'm going to do. Unfortunately, there's 4 of them, so we have to plug all 4 in because the parabola and the circle are going to intersect 4 times, just like where I drew it up above. Mine intersected 4 times. Not necessarily going to do that, but in this case it is if we have 4 different x's. Okay, so I'm going to have to do this on my next page. To find the ordered pairs, I can pick either that equation for the circle or the equation for the quadratic. It doesn't matter which one I pick because the ordered pair for when x is these 4 values is going to be the same for both of them. So that's why it doesn't matter. If you don't believe me, pick one and then pick the other and simplify and see if you get the same thing. I'm probably going to pick the quadratic just because there's less squaring going on, but you could pick the circle if you want to. But I have to plug each one of these x's into one of those equations to figure out the y, so we have the ordered pair. Coolio? So I'm going to do that on the next page. So I am going to first say when x is, I got to do when x is 3, when x is negative 3, when x equals 2, and when x equals negative 2. And for each one of those, I'm just going to plug them all into the parabola equation. X squared minus y equals 7. And I'm going to do that quietly because y'all don't need me for this. Just make sure you get what I get.
That's not what you're doing.
Silly.
I'm sorry.
My laugh is quite
This one, this one.
Oh.
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 What?
Ladies.